Hey, welcome to Mr. Nice's calculus video. Today we're going to move on from some limit stuff we've talked about, and we're going to start applying some properties of limits. The first thing we're going to talk about is continuity. And we're going to use limits to prove continuity. So let's look at some basic examples. Some visuals to start here. X and Y axis. Here is a graph. Boom, that is continuous, right? There's no breaks in the graph. That one's good. Continuous. How about slightly different one that looks similar? We'll go through here and create a hole this time, but we will have the y value, the x value filled in. So the domain is still all real numbers in this case. However, the range kind of gets a little hiccup in here. Okay, this is not continuous as it has a hole. Okay, it's got what's called hole discontinuity. Discontinuity. All right, how about one more example here? So now let's go and create a hole again. And actually that's a bad function there. Not a function, doesn't pass the vertical line test. I'm actually going to undo that one there a little bit and see if I can make it. There we go. And now this one will head up here and go off into the distance. Alright, so this also is not continuous. It has what is called a jump discontinuity. Jump discontinuity on that one. Right, because it jumps from here to there, boing, like Mario Brothers. So now let's look at a formal definition for limits, or for continuity. All right, definition. I guess I need to go off of black. It's not going to work on a black background there. So definition. F of x is continuous at x equals c if there are three criteria. Criteria number one, f of c must exist. In other words, if I plug c in, I better get a value out. So let's label this guy here as c. We'll call this c, and we'll call this c. So, yep, sure enough, there's a y value there. That one fits. No, but yes, there. So f of c exists, and again, f of c exists. So all three of them meet the first criteria. The second criteria is a little more strict. The limit as x approaches c of f of x must also exist. Okay, that must also exist. So if I take the limit from the left, check, and from the right, check. Both head to the same spot there. This one, limit from the left, yep. Limit from the right, yep. Both heading to the same spot there. This one from the left is here, and from the right is here. So in the third example, it does not exist. Okay, the limit from the left is not equal to the limit from the right, so therefore the limit does not exist. All right, and the third criteria, so in other words, this one's being eliminated already by criteria 2. The third criteria is it's not good enough for the function and the limit to exist, but the limit as x approaches c of f of x must equal f of c. Okay, so that's the final and third criteria. So let's look at this one. So we said f of c was this value right here. We also said the limit as x approaches c was that value. So this is continuous. They all meet up right there. This one, however, the limit as x approaches c is right here. We'll call that a. And this is up here at some b value. So while, yes, the function exists at c and the limit exists at c, the two are not equal to each other. Therefore, it fails criteria 3. This is not continuous. Let's look at some examples of functions. All right, f of x equals 1 over x. Well, hopefully we know what that graph looks like. But regardless, the issue is that x equals 0. So our c value, c will be 0. Okay, so I need to determine, does f of 0 exist? No. Okay, so it is not continuous. Right, I cannot plug 0 in here. I can't divide by 0. Let's try another example. G of x equals x squared minus 1 over x minus 1. So here the issue is 1. So c equals 1. Does f of 1 exist? Again, the answer is no. If I plug 1 in, I get 0. But somebody might argue, well, I can factor the top into x plus 1, x minus 1. And then I can cross out x minus 1. Well, that's all fine and dandy, because I can say the limit as x approaches 1 of g of x is equal to 2. However, the function value still does not exist. So again, not continuous. Third example, everybody's favorite piecewise functions. So we'll look at x plus 1 for all values of x less than or equal to 0. And we'll look at x squared plus 1 for all values of x greater than 0. So for this example, to find what our c is, we just look at the individual pieces. X plus 1 is just a line. We all know that. Lines are continuous. X squared plus 1 is a parabola. We all know, excuse me, we all know that. Parabolas are also continuous here, so the issue isn't with x plus 1 or x squared plus 1. The issue is where the two meet at 0. So c will be 0. So does f of c exist? Well, when x is 0, I look up here, or equal to. 0 plus 1 equals 1. So criteria number 1, check. The limit as x approaches 0 of, and that should be an h, right? h of c, of h of x. Let me just change this guy into an h, or the appropriate letter there. There we go. The limit as x approaches 0 of h of x. Well, that's a little trickier. I need to come from the left-hand side and the right-hand side. So if I'm coming from the left, that's value smaller than 0. Plug a 0 and I get 1. The limit as x approaches 0 from the right-hand side, that's values greater than 0. Again, 0 squared plus 1 is 1. Therefore, the limit itself exists at 1. Right? The left and right both meet at 1, so the function's limit is 1. Now thirdly, so check, we've done criteria number 2. The third criteria, does the limit as x approaches 0 of h of x equal f of 0? And the answer is yes, they both equal 1. Therefore, this is a continuous function. Alright, so a couple tests you got to apply. Piece of cake, not too bad though. Alright, one other piece we're going to talk about here today is continuity on a closed interval. Continuity on a closed interval. So the same reasoning applies. The difference here now is I'm not looking at a graph that has arrows on either end of it, right? Not one that goes on forever. I'm looking at a piece that starts here and ends here. It's on a closed interval. We'll call it AB. Okay? So we've mentioned we don't have two-sided limits here. I only have a one side. I can only come from the right-hand side here. Right? And this side I can only come from the left-hand side. There's nothing over here. So technically the limits do not exist at A and B. So that means it would fail the second criteria for continuity. However, when you're on a closed interval, there is a special rule for is a function continuous. So a function is continuous on a closed interval from A to B if it is continuous on the open interval. All right, we use parentheses for open and brackets for closed. So continuous on the open interval, and the limit as x approaches a from the right-hand side of f of x is equal to f of a, and the limit as x approaches b from the left side of f of x is equal to f of b. All right, then we have continuity. So what that means, if I approach from the left, that gives me f of a. Sorry, from the right. And likewise up here, that gives me f of b. So this is continuous on the closed interval. Obviously, it's not a continuous function because it doesn't go on forever. But it's continuous on the closed interval. What would something that's not continuous closed interval look like? Well, you don't see them very often, so this does not end up being a huge topic in calculus. But let's say we have an open circle and then close the other end. And you might say, wait, that's not a closed interval. Ah, I'm not done. Now I've just closed the interval, right? It starts at some a value. It ends at some b value. Okay, so this is a closed interval from a to b. On the open interval, from here, right, I'm not at the open circle, but here, all the way up to that point right there, right before that, it is continuous. There's no jumps, there's no gaps. You can go on the left and the right of everything. Okay? But when I look at my limits, my one-sided limits at the endpoints closely, as I approach a from the right-hand side, I do have a function value here. We'll call it c, or a limit value. But my function value is up here at d. So while the limit exists at c, the function value exists at d. So therefore, the limit as x approaches a from the right of f of x does not equal f of a. Therefore, this is not continuous on a closed interval, whereas this is. All right, and we'll discuss some of that a little more in the future. There's a quick look at continuity and continuity on a closed interval. Hope you enjoyed today's video.